We are interested in energy conversion. It's in nanoscale, and I would like to make a few comments what nano potentially can do to energy conversion. In general, you don't think that there is an immediate and obvious benefit when it be small. Why should it help energy conversion? And I would like to give you a few arguments. And instead of bombarding you with a lot of slides, I just use a few simple figures on the board. And then I also want you to listen to my postdoc and former student, Neil Dasgupta, who I'm very pleased to have here this morning, because you have to keep in mind that's the biggest pride of any faculty member, to have successful and bright students in their group and then see them succeed in their own career. So that's why I brought Neil today, because I think he has a bright future. So energy conversion is very interesting because you have two key arguments to consider. The one is an equilibrium argument, and the other one is a non-equilibrium argument. And that's true for virtual electrical energy conversion process, whether it's a solar cell, whether it's a fuel cell, or it's a battery. In all cases, there's an equilibrium state, because in all cases, what you do is you change, and when you talk about energy conversion, you take a system from one energy state and you put it into another energy state, whether you go up or you go down. In both cases, you're transferring. Those are two equilibrium arguments to where you go from one equilibrium to another equilibrium. And then what you have to consider, there are some barriers in between. So in any energy conversion, you're talking about going from one state to another state, and you have some barriers you have to encounter in between, and that barrier limits the kinetics of the energy transfer. So what you would like to do, you have to worry about this, and you have to worry about that when you do energy conversion. This is largely related to the losses. And to quantify an energy conversion system nowadays, we are mostly concerned about energy conversion from a chemical state to an electrical state. We are talking about electrification of cars. So ideally, you would like to take energy states and in the process convert it directly into electricity. That's not the way how a car works today. In a car, obviously, you take chemical energy directly into mechanical energy. And that has limited conversion efficiency, and I'm not going to talk in the details of limited conversion efficiency. You're limited by the Carnot process and a lot of other issues. We would like in the future, you will see a lot more direct electrical energy conversion, where you take a system and you directly convert by going from one state to another. You directly convert it into electrical energy. And how does this look like when you look at the voltage in energy conversion versus the current? So let's assume we plot here voltage versus, instead of current, let me call it current density. Then in general, it looks qualitatively like this. So there's an equilibrium voltage, like in a battery. For that matter, it's true for a fuel cell, and it's true also for a solar cell. You have a certain starting voltage. We call this an open circuit voltage. When you draw almost a very, very small current, how much of a voltage do you get out? Battery, solar cell, fuel cell, it's all the same. And then as you draw a larger and larger current, your voltage goes down. You probably have seen that when you buy yourself a battery and you draw a current from this battery, the more current you draw, the smaller voltage output you get in return. And what you, from a scientific point of view, you need to understand this quantity, this intersection. We call this the OCV, the open circuit voltage. And you also need to understand then the kinetics as you draw currents. Why do you lose voltage? And as an engineer, what you would like to, obviously, you would like to keep this as high as possible. And you want to keep this slope as flat as possible. This is obviously not good. What you would like to do is you would like to have that. So you need to engineer the system such that when you draw a current or a current density, that you lose as little voltage as possible. And that's, for example, where the size argument comes in. Size, that's why we're talking about nano. Nano can help you influence the open circuit voltage. And size can also help you influence the transport behavior, the kinetics, the losses associated when you move charges in a device. And nanoscale, to give you a very simple example, the further you have to move a charge, the greater the loss. It's like resistance. When you drag something, there's a resistance going along. And the shorter distance you have to drag the charge, or whether it's an electron, whether it's an ion, it doesn't matter. The shorter the distance, the fewer the losses. Naturally, a short wire is always associated with fewer losses than a long wire. In the case of a battery, or in the case of a fuel cell, or for that matter, in the case of a solar cell, the shorter the transport length, the fewer the losses. So there's an inherent advantage whatever device you have in the conversion process. If you can minimize the transport losses, the greater the efficiency of the system. And that's inherently associated with, that's why in my laboratory we were building devices at the nanoscale, because it's in nanoscale, well, you can just jump a few atoms, 10, 20, 30, 40 atoms, and that minimizes the overall losses. That's one aspect, but not the only loss. That's not the only aspect. The other one is associated, as I said, with the equilibrium quantity. The open circuit voltage is is an equilibrium quantity. So even if you draw very, very little current, or almost no current, there's a certain open circuit voltage associated with, which is an equilibrium quantity. That voltage exists. That's a potential, which you can measure by drawing a tiny, tiny current. That's how we always measure voltage. There's no way to measure voltages directly. The way you measure voltage is by drawing a tiny, tiny current. And so that's how we can establish the open circuit voltage. And again, you have an open circuit voltage in a solar cell, in a fuel cell, in a battery. And these are an opportunity for tuning the open circuit voltage as well. There is. For certain processes, it's just determined by the chemical reaction. There's nothing you can do. But for example, in a solar cell, you can tune the absorbing material. What you can do is you can, as you know, there's an interaction between the incoming light and the material which absorbs the incoming light and converts it to an electron-hole pair, because that's what the light quant does when it enters a piece of material. It splits, it excites an electron from its ground state to an excited state. So it goes from what we call the valence band to the conduction band. And there is a certain energy barrier associated with that. And the height of that energy barrier is, in a solar cell, is related to open circuit voltage. And that height of the energy barrier to bring an electron from its valence band to conduction band can be tuned by the size of the absorbing material itself. So it's very interesting that if you make very, very thin structures, and I'm talking about a few nanometers, there is the opportunity to tune that thickness to the energy or to the wavelengths of the incoming solar light, which is required to take this electron from its ground state or from its valence band into the conduction band. And with that, you can influence the OCV in a solar cell. So all I'm giving you is I'm giving you a few qualitative arguments why size is important. Size is important for example, in a solar cell where you can play with tuning the incoming light and getting the electrons excited. And the slope of this characteristic curve is related to the transport, to the kinetics. So as I said, in any energy conversion, you have to worry about the equilibrium, this quantity, and you have to worry about the kinetics. The slope of that curve is the specifics of this curve all differ for a battery, for a fuel cell, and for a solar cell. And obviously that is the subject of a quarter-long course to understand the specifics and model and understand the specifics of that shape. But there's one thing for sure: as a current goes up, the voltage goes down monotonically. That's true for any energy conversion. And the equivalent in the mechanical world is true too. In the mechanical world, when you talk about an engine, you could plot pressure or pressure ratio versus, say, the power you draw out, whether you talk about RPM or whether you talk about the speed of the engine. So in that case too, ultimately, the faster the engine turns, ultimately the pressure goes down. So you can make even the equivalent consideration for a mechanical system as well, not only for the electrochemical equivalent. So you have this relation between voltage or pressure and current, or in the mechanical system, flow. The flow of gases or whatever the exhaust stream might represent. So I have a few more minutes to talk about this curve, because ultimately what you're interested in is power. And how does power relate to this curve? Power is a product of voltage versus current. And when you have no current, you have no power. And when you have no voltage, you have no power either. For example, here, there's no power. So you can imagine there's a peak in between. If you multiply the voltage with the current, there's obviously some peak. This is where the peak power of a system is. The peak power of a system is not necessarily related to the maximum efficiency. And my question to you is, on this curve, where is the point of maximum efficiency?
At low current. At low current.
It's a low current, exactly. So these are all the losses. So when you take the equilibrium, this is essentially the loss, and it's a low current. That's the point where we have maximum efficiency. So for example, if you have a, say, in a natural system, in a biological system, we also do energy conversion all the time. We eat, and we oxidize the sugars. And the way we oxidize the sugars is by inducing a certain ion transport across the membrane. And whether it's in a plant cell where we have the thylakoid membrane, or whether it's the inner membrane of the mitochondria, in all cases, we transfer material across a very, very thin membrane. Nature is very, very good. And nature wants to be also very efficient. So in order to be very low on the current side, what does nature do? To have a system like our body, to transfer energy or to convert energy as efficient as possible, guess what would you do? To go very slow.
I mean, it spreads out the metabolism among all the different cells in the body.
That's correct. You need lots of area. And that's exactly what you have in biological cells. You have lots and lots of cells if you actually convert you try to convert it into a membrane. We have square miles of membranes in our body in corrugated structures to be as efficient as possible. So here is a good argument why you want to be thin and why you want to go slow. So when it goes thin, which nature does, the membranes of our mitochondria is very, very thin. So you're seeing nature's evolution has done exactly that. So you be very, very thin, and you transfer only a few atomic layers. And that's what you're trying to do in a fuel cell. But to be efficient, you also want to go very slow, which means you have to have lots and lots of surface area. And that becomes ultimately, if you talk about the system which you want to build, it becomes an economic argument. Obviously, the larger area you have to make, the larger membrane you have to produce, the more cost is associated with that. But at the same time, you can be more efficient. So you have to consider, from an optimum point, what's the best system to design. So that's really all I wanted to say is, whenever you do energy conversion, there's an equilibrium argument, there's a kinetic argument. you need to consider both, and size matters. If you're small, you can reduce the kinetic, you can reduce your losses as you transport the charges, and if you go slow, you can also help quite a bit. In addition, there's a size argument, including the equilibrium argument, particularly in the solar cell, and that's what Neil Dasgupta in his PhD thesis, which he finished recently in his now postdoc in my laboratory, that's what he studied in his PhD thesis. So maybe at this point in time, we can say a few words about what he is doing.